On the 22nd of March, we will celebrate World Water Day. And this year's theme is Groundwater, making the invisible visible. And you can help making the invisible visible too. Grab your phone or camera and show how groundwater affects your daily life. Is there enough? Is it safe to use? Who uses the most groundwater in your area? And what needs to be done to exploit and protect groundwater? The 5 most compelling stories will at the end of the year be shown to over 300 policymakers at the UN Water Summit on Groundwater. You can have your voice heard and make a difference. So, how can you join? Shoot the video on landscape orientation. Go into the field and show your groundwater story. Use a mic for good quality audio. Keep your video respectful and keep your video to 60 seconds or less, unlike me. And follow these 3 steps. Upload your video to YouTube or Vimeo, then share it on social media using these hashtags and send the video link to this email address. Good luck, together we can make the invisible visible.
Okay. Good morning, everyone in the Philippines, and good evening. Good evening, probably in other parts of the world. Welcome to our webinar, PASA webinar on groundwater, making the invisible visible. So this PASA webinar is organized in celebration of the UN World Water Day 2022. Thank you for being with us today, and thank you for waiting. We actually we are expecting over 80 participants, but probably it's too early and they are not yet here, so we have to begin our program right away. Okay, so to welcome our webinar, to welcome you all, may I call our PASE President, Mario Santo Domingo, all the way from Baltimore. Good evening there, Mario. Okay, I think you are muted. Okay, wait a moment. Wait a moment, Mario, you are muted. Okay. Okay. I think you are not assigned. Okay, yeah, sorry.
Hello, can you hear me now?
Yes, yes.
Yes, so good morning to everyone. So I'm Mario Santo Domingo, the president of the Philippine American Academy of Science and Engineering, or PAASE. PAASE is a 42-year-old organization of scientists and engineers of Filipino descent. Most of us are actually based either in the US or the Philippines. So I'd like to thank the organizers of this Friday webinar, especially Dr. Marla Redias of De La Salle University. This has been a very important issue for me. You know, one of the most popular general education courses in the university where I am a research scientist is called Water, an Interdisciplinary Study. So it's an interdisciplinary lab, a science experience that integrates chemistry, biology, physics, and earth sciences. And I connect this popularity of this class to findings in psychology and learning research that people have a very strong affinity with water. And among children, water play or activities around water enhances cognitive development. In my case, I grew up in a place just a stone's throw from a river, and I often visit my relatives, like crossing Laguna Lake. And so I had a really very practical experience with water. But whether you're experience is theoretical or practical, we need to make the discussion and the conversation around water more often, because this is a very crucial topic. Water conservation, water depletion, and the different categories of water. You need to educate us, laymen, about water and its importance, and what we can do, to be able to contribute to problem solving related to issues about water. So I won't be speaking for long. I would like to welcome all the participants in this morning's activity. Good evening from here in Baltimore. I'd like to thank all our esteemed speakers. And of course, I'd like to thank again Dr. Marla Diaz for this very, very important event. Thank you, and may we all learn and enjoy this session. Thanks.
Thank you very much, Mario, for that welcoming message. And now I think we can begin our webinar with our first speaker. Okay, our first speaker topic, he is going to present about visualizing groundwater, a scientific approach to groundwater security. Reggie Makashib is an assistant professor at the University of the Philippines. He pursued his Master of Science in Environmental Engineering, specializing in water quality management, and he studied the fate and transport of heavy metals in Agno River surface water and sediments from UP Diliman. And he became a part of the Environmental and Energy Engineering academic group. And among the undergraduate courses, he taught sanitary engineering, technology, environment, and water quality analysis. His research revolved around water quality management, including surface water and groundwater, water quality modeling, GIS applications and environmental management, soil and sediment quality assessment. And he was involved in groundwater modeling and management projects with the National Water Resources Board as technical assistant in 2015 and 2017, and also involved in a project called Philippine Electrochemical Arsenic Remediation, or PhilECAR, that aims to implement a novel technology to remove toxic pollutants from groundwater use for drinking purposes. So let us welcome our first speaker, Reggie Makashib.
Well, good morning, everyone. Share my screen. Okay, so again, good morning, everyone. I will kick off today's webinar, and my talk today will literally take on the theme of the webinar, making the invisible visible, because I will talk about the different scientific approach in order for us to visualize groundwater. And what I will discuss today is generally the workflow used to apply these different scientific approach, but I would want to focus on their actual application. Hopefully, at the end of this talk, some of you, I see there are students here and some water managers here among our participants, will have an interest in groundwater research, particularly in groundwater modeling. Okay, so we need this scientific approach because we recognize that groundwater is a hidden resource. And compared to surface water, for surface water, it is easy to see the availability, the current state, to assess the quality of surface water because you can see it. Just a couple of days ago, I heard from the news that the level of water in our reservoir is below the normal operating level. So right then and there, when you hear that, you know that probably in the coming days or weeks or months, we might experience water supply problems. But with respect to groundwater, we do not hear reports such as the current water level below the ground is like this or like that. Despite the fact that 50% of the Philippines are dependent on groundwater and 85% of the piped water supply uses groundwater as a source. So for us to properly manage groundwater resource, we need to know what's going down there in the subsurface to create effective policies about resource management. And when it comes to making policies, modern water management environmental problems require new scientific and evidence-based approach. The figure here shows the different approach that can be done. Some of these is being implemented now, starting from the monitoring. Right now, in the Philippine context, the National Water Resources Board, I believe, is already installing different groundwater monitoring network all throughout the Philippines to know or to gather real-time data about our groundwater. Monitoring alone tells us what's in there in that specific point where we monitor groundwater. But from that data, from that raw data alone, we cannot make sound decisions. So we have to move forward to a more proactive approach, and that is by mapping and modeling. So these two usually come together. When we map, we can see how does it look. And when we model, we try to answer how did it become like that? If there's a saltwater intrusion, how did the saltwater intrude from the seaside to inward land? Okay, and right now the current research direction is aimed towards predictive modeling, that is answering questions like what if through scenario analysis. Knowing those things, what could have been through uncertainty analysis. So these two seem to be similar, but actually uncertainty analysis takes into account the probability, the likelihood of a scenario happening, whereas scenario analysis simply tells us the possible outcome, okay, without consideration or without thinking a lot about how likely or how reliable a specific decision or management measure is. And we have optimization problems, which answers what is the most effective decision or measure, considering all the constraints, the decision variable, and other decision criteria. So altogether, this is predictive modeling. So I will discuss first what we are currently doing, okay, at least in the context of the Philippines, and how we can move forward in the future, because this is the future of groundwater management. Okay, so monitoring is a reactive approach because, as I mentioned earlier, knowing simply the data, we cannot make sound decision. Okay, we cannot picture the entirety of our groundwater resources. Okay. And the predictive modeling is the more proactive approach because we are trying to model what could be the state in the future and try to make policies out of that in order to prevent future problems. Okay, so as I mentioned earlier, then I think the NWRB is already in the process of installing different monitoring networks in the entire Philippines, and I'm happy. I just discovered this recently. Well, not recently, maybe a year ago, more than a year ago. We have now an online database of the real-time well monitoring data. So you might want to visit this site. I'm not connected to this project, but I'm just happy that we finally have this database wherein we can see the overview of the groundwater resource through the real-time well monitoring data that they are collecting. But as I mentioned earlier, that is a reactive approach. Looking simply at the data that are collected, we cannot make decision because as humans, we want to see what's in there, right? So the direction from monitoring, it has become towards the mapping and modeling. And through maps, the groundwater managers will now be able to answer questions like this: where are the anomalies in groundwater quality? And if we know what particular area what particular area experiences those anomalies, maybe we can design further studies to investigate that particular area, which areas experiences problems, what adjustments could be done in the extraction and treatment operations, and so on and so forth. So these are some of the management questions that we seek to answer. This is an example of our study. This was in Dasmariñas, Cavite. Okay, so as an output of this, we made recommendations to the local water district that these are the areas you need to look into. Okay, an extension of or an application of mapping is the vulnerability assessment. One such tool is called the drastic method. This was proposed by Aller and Bennett in 1987. The method is actually old, it's 1987, and it involves a series of maps or layers of maps, 7 layers specifically. Each of the drastic acronym corresponds to one map. Okay, so D for depth of groundwater, R for recharge, A for aquifer media, S for soil media, topography, impact to vadose zone, and C is hydraulic conductivity. Now we put this together to create a vulnerability map. The objective is again to find out where the vulnerable regions are so that we can focus our remediation measures to that area. So this method is a ranking and weighting system. So each of the layer has a corresponding rating. Okay, so depending on the hydrogeologic characteristic for each layer, there is a corresponding rating recommended by Aller and Bennett. So you will assign that rating, you will multiply each to the corresponding weight for each of the layer to have the total pollution potential of that aquifer, that groundwater. Okay, so this is one example of what we did for Metro Manila. We were able to find the identify the vulnerable areas. And another example is here in Pampanga. So I apologize, the choice of color here, the red here does not mean high risk. Okay, so that's moderate. Blue is high. We should have interchanged the colors. Okay, so using these tools, the groundwater managers, again, would know where to focus our attention to protect the groundwater, in which areas could still withstand further environmental stressors. Okay, so those are some examples. There are many other vulnerability assessment tools that you can find in literatures. And most of them, of course, will involve the application of GIS. But most of the problems, management problems, has to address, or the management decisions has to address the whys and the hows. So those tools only tells us what it looks like, where are those anomalies, where could we focus it, where we could focus our attention to. But most decisions have to answer whys and hows. Hence, the modeling process is being integrated now in groundwater management. In other countries, I don't know in the Philippines, but in other countries like Australia, South Korea, the water companies there are already investing on the model, on training their staff to do the modeling, and they're also investing a lot of money to develop their own models for their particular service area. So generally, the modeling process is like this. Okay, so I adapted this from this paper. So if you want to further read about modeling, you can read this paper. So basically, we have a simulation code, the software. In that software, we set up the conceptual model in which we try to mimic the actual aquifer system or hydrogeologic structures. However, we simplify it because the reality is that it is very complex. Okay, so we try to simplify it. We assume parameters based on field data. We add external forcing functions like rainwater, river stages, river heights, river flows, and we impose a past state or an initial condition. Then we let the software to do the simulation to show us the future state or the present state of the groundwater resource. Now, the problem with modeling is that there are a lot of data involved here. So you can see here we have this geometry. We need to set up the geometry of the aquifer. We have this data. We need to know the concentration, the initial concentration of chemicals, for example, the hydraulic head. We need to have data about the time varying external forcing functions. Okay, so in order for this future state to be as close as possible to what is there on the ground, we have to come up with a good combination of all these parameters through calibration. And the common method of synthesizing those data is listed here: manual, insertion, direct, and indirect. But commonly, the modelers would use the manual insertion and a direct method, which means that if you have a lot of data, you can somehow infer the properties of the aquifer, okay, and then you can input that to your model and let the model do the work, okay. But the problem is that assumption, or those assumptions, are hit and miss. And so recently, there are new methods being developed to integrate the uncertainty in those parameters. So that initially the parameters and the model structure would be somehow accurate enough in order to provide a simulation that is as close as possible to the actual, or to the reality. Okay, so this is an example of what we did in one project. This is by manual insertion. So we have a lot of data. We infer from those data sets about to make a model. Okay, so these are all the inputs to the model. And these are some examples of the raw output that we have. So we were able to visualize how the groundwater flows through the region, the direction, the velocity, the hydraulic head. Okay, in order for us to address these questions that were thrown to us by the proponent, or the NWRB specifically. So how does groundwater change seasonally? Which areas most likely experience a groundwater supply? Where should monitoring wells be constructed? If there are migration of contaminants, what is the direction of migration? How can we prevent that? And so on and so forth. Okay, so that's the advantages or the use of modeling. We can now explain why this happened. How can this be prevented? Okay. However, the decision making is not still integrated into the model. What I mean is, if you have a groundwater model, if you want to predict what the future state would be, okay, you have to extrapolate conditions. Say, for example, if you want to incorporate the effect of climate change, you have to modify the possible future recharge conditions, rainfall, and so on. So you have to rerun the model manually to account for the various cases, to cover all the possible scenarios, because you are now recognizing that there are uncertainties that could arise with all of the assumptions made in the model. However, the human mind is not capable really of randomizing or dealing with uncertainties, right? So when you do this manual iterative process, and then you attempt to cover all possible scenarios, the common practice is to assume the optimistic and the worst case scenario, particularly in external forcing function, in order to cover all possible scenarios. So basically, the decision process is not incorporated. So the model will simply give you the result, and it's up to you to interpret it. You post-process it to make management decisions. And that process itself is time-consuming, computational demanding, and it is a trial and error process, because you are trying to, again, to cover all the uncertainties in the model. So the risk is unknown. The reliability of future management decision would be unknown in this process. So the future direction or the current direction of research towards predictive modeling is to come up with algorithms or new technologies or new processes, new softwares to balance these three: decision variable, constraints, and objectives, while being aware that there are uncertainties in the input and how to deal with those uncertainties so that you have an optimized output, okay, with high reliability, with decisions that are highly reliable. Okay, so before we could go to that direction of formulating new methodologies, new algorithms, we have to understand where are our uncertainties coming from. Okay, structural uncertainties coming from the simplification of complex word process, the parameter estimation, as I mentioned earlier. The reality is that the parameter values are complex. Okay, it is widely varying in the real world aquifer. So you are simply making a point estimate of one specific region, one specific layer. So there are many uncertainties on that. Data caused by instrument device error, extrapolation errors, specifically when you are trying to expect or when you are trying to cover the worst case and the optimistic case scenarios in the future. Okay, so how are these uncertainties incorporated in the models? The current or the approach is to treat the model parameters as having prior distribution. So this involves some statistical analysis, particularly the Bayesian inferences. I'm not going to discuss the specifics of it, but if you want to do further reading, if you're interested in uncertainty modeling in groundwater, you can further. There are many papers that you can read that applies common algorithm techniques such as Monte Carlo algorithms, swarm theory, meta-heuristic algorithms, and data assimilation techniques to incorporate those uncertainties. So again, I will not discuss the theory behind, but I will show you how this is applied in a real-world problem later on. So predictive modeling, we try to balance the decision variable, objective, and constraints. Okay, so the decision variable are input to the model that is controlled by management action. This in, for example, the extraction rate, how much can we allow the extraction rate for each well to be. Okay, location of new wells if you are permitting new constructions of wells, quality parameter, pumping water level, etc. Constraints are conditions derived from decision variables, such as we limit our extraction rate to this value, the drawdown to this value, and so on and so forth. And objectives are results from the interaction of decision variables that is optimized. So we want to maximize the extraction rate to meet the demands. We want to optimize the location of new wells so as not to result to excessive drawdown or excessive pumping of water. And yeah, the objectives are like that. So one application of this is a very classic problem, the Henry problem, wherein just to show you how this this algorithm or this tool is used in making decisions and how the decision process is incorporated in the modeling. Okay, so the problem here is to design an artificial recharge basin to mitigate the landward migration of saltwater freshwater interface under increased extraction. So this is the upgradient boundary, meaning the landward side of the aquifer, and this is the seaward side. So this is the boundary of saltwater freshwater. So we want the problem is to not let this boundary reach these extraction wells. Okay, so this particular problem was applied by White, was particularly used by White in a new approach, modeling approach for multi-objective optimization under uncertainty. So what are the decision variables, the location must be between 1 to 140. So the recharge area must be within this area, 0 to 140. Okay, the rate of artificial recharge is also constrained. Concentration of recharge should be between this. The extraction per well is this. There you have the objectives. We want to maximize the artificial recharge basin distance, meaning this area here. We want to minimize the artificial recharge rate. We want to maximize the artificial recharge concentration and maximize the combined extraction from 3 wells because we want to meet the demand being supplied by these 3 wells. Okay. And the constraints are, the constraints could be the environmental constraints or the policy constraints in that area. So these are just some examples. So we incorporate the input uncertainty, particularly on the properties of the aquifer. We incorporate that, input that to the model, to the predictive modeling by PEST, and using C++ language, programming language, to optimize the output. So what I'm saying here is that you don't need to iterate the model because to iterate the model manually because the tool itself will do the decision making for you. In what sense? Because the output of this particular model will tell you the optimum decision to be implemented, as well as the corresponding risk and the reliability of that decision. So this is just an excerpt of the wide array of graphs output of this model. The dots here, the dark blue dots depict the risk-tolerant or low reliability measures, and the yellow dot here depicts the risk-averse high reliability solution. So the management decision is to balance the extraction rate and the recharge rate so that we can meet the constraints as specified earlier. And from this graph, you can see if we want to be highly reliable, if we want to be risk averse in our decision, so we will choose measures or decisions in this region, in this yellow part. So there, for each graph, there's each dot here corresponds to a value of recharge salinity, extraction rate, the location of the basin edge, okay, and so on and so forth. So if you want to be risk averse, then for this particular problem, we have to limit the extraction rate from 0 to probably 2.5, the recharge rate from 0 to 5. So you can see now we have now a range of values that can be used or that can be implemented instead of one or two or a couple of acceptable values when we do the manual iterative process of the forward model. So 0 to 5, recharge rate, the basin edge or the recharge basin should be limited to this, to 0 to 100. We go back here. So your recharge rate must be up to this point. Okay, so this area here or this segment here can be assigned as a recharge rate. Okay, the beauty of this method is that you now know the corresponding risk. So probably if you want to be very successful in your decision, you are risk averse, then you have the option to do or to choose those decision variables. If you want to be a little bit risk tolerant, then you may choose to implement values around this area. Okay, so around the blue-green dots. Okay, so now with predictive modeling, we have incorporated the uncertainty. We have managed our expectation in the future because we know the corresponding risk of the decision that we are making. Okay, so this is a very new research direction, and particularly the different algorithms, the different softwares that are being developed. And I hope Our researchers today and groundwater water managers will have an interest in exploring this side of groundwater modeling, the predictive modeling, because this is the future of groundwater management. Okay, this is the proactive approach of groundwater management. Okay, so that's all. If you have any questions, you are free to ask your questions. Thank you very much.
Thank you very much, Sir Reggie, for your excellent presentation. And so we would like to, I believe there are questions from our participants today, but let's proceed now with our second speaker. Later on, let's have time for our discussion. Okay, Sir Reggie, if that's okay.
Thank you. Sorry for it.
Yeah. All right. So our next speaker he is currently the Strategic Asset Management Advisor at the Manila Water Company Incorporated, and he is responsible for the reconstructing and managing the operations of Manila Water's pump stations, filter plants, primary network, and telemetering and dam facilities. And also, he directed the improvement programs of plant facilities in terms of reliability, safety, and maintenance. He is instrumental in the achievement of water supply, 24-hour water supply for the East Zone concession, and also managing the water crisis brought about by El Nino during the previous years. He spearheaded the development of new water sources for Manila Water's business development and take lead in the review of Manila Water's major infrastructure projects to ensure it is fit for the purpose and aligned with the company's business plan. So let us welcome our next speaker, Mr. Noel Abesamis.
Yes, good morning to everyone, and thank you for inviting Manila Water to this event of celebration of the UN World Water Day. In behalf of Mr. Abi Basilio, wait, I'll just be sharing my slides. Okay, so hope the slides is already shown on your screen. So in behalf of Mr. Abi Basilio, who is our Chief Operating Officer, we would like to thank Dr. Marla Rodillas and also the Philippine American Academy of Science and Engineering for organizing this event. So thank you very much, and we would like really to participate in this wonderful event of making known the water sources, not only in the Philippines, but all over the world. So the theme of our webinar for today is groundwater, making the invisible visible. So in this presentation, I would like to share with you the 24-year story of water sources of Manila Water and how groundwater fills the gaps in the supply demand, and also to present to you the short and long-term initiatives of Manila Water for its groundwater sources. Okay, so as a backgrounder, it is very important for us to understand the baseline information where Manila Water started. Prior to the assumption of Manila Water in the operation and management of water supply in Metro Manila in the East Zone, Metro Manila gets its water supply from Angat surface water, contributing to around 97% of the total supply of Metro Manila comes from Angat, and around 3% of that supply comes from groundwater in 1997. And also, in 1997 or prior to 1997, prior to the assumption of Manila Water, Metro Manila at that time has only a coverage of 67% of its total population. And with water availability of only around 16 hours per day, and of those 67%, only 26% is experiencing a 24 hours water supply. The non-revenue water, or the water that is being lost during that time, amounted to as high as 63% with a very poor water quality. That's why there's a high incidences of waterborne diseases prior to 1997. So in 1997, the Metropolitan Water Works Sewerage System privatized the operation and management of the utility while maintaining the ownership of the assets to the government. The framework is based on the Build, Operate, and Transfer law that was enacted under Republic Act 6957. And this framework gave us the basis for privatizing the utility and bidding it out to different international bidders. And these frameworks also allowed the concessionaires, which the private utility that won, to put investment for the construction, operation, and management of infrastructure. And after a period of engagement that is around 25 years, those assets will be turned over to the government. I think this is a very good partnership with the government. And in fact, we would like to show you the results after those 25 years of the PPP. Actually, it is only up to 20 years, 22 years. After its having the operation and management in 22 years, we would like to show you the results. So, as you can see on the slides, Manila Water achieved more than double the number of customers that can avail of its water services from the start of 3.1 million customers in 1997. In 2019, we are now already at 6.8 million. Sorry, the slides I have provided is only 2019 because there's pandemic on 2020 and 2021. I cannot really get the whole picture as of today, but this is only up to 2019. And it has also improved its water services by increasing the water availability to its customers from 26% to 100%. So all of those customers that were connected to the pipeline of Manila Water has been receiving a 24-hour service since 2006. And much more, the operations efficiency has improved, surpassing the global standards of non-revenue water from 63% to as low as 10%. Okay, we will show you in the succeeding slides the events. In terms of pipes laid, Manila Water had laid 5,112 kilometers of pipelines in the distribution system for all of those years. In terms of volume saved due to non-revenue water program, Manila Water saved around 700 million liters a day, which is equivalent to a big dam. The one that is being developed right now by the government is the Kaliwa Dam, which is only 600 million liters dam. But on our non-revenue water program, we have saved around 700 million liters a day. And in terms of customers benefited by these programs, from 440 million liters a day that is being delivered to the customers in 1997, we are now delivering around 1,357 MLD to our customers. So let me share to you how the progression of the water source for Manila Water. So from the slides, this is from a time-based slide from 1997 to 2021. You could see the chart. The light blue one represents the average water demand requirements of the system, while the dark blue one represents the water requirements during summer. So the one is the average, but during summer, which is from March, April, May, we have a very high demand due to hot weather system and people wants to use water. So basically, as you can see from the chart, there is not really much difference from 1997, only around from 1,300 to 1,600 million liters a day increase. And looking at the available water supply, the water sources that we have the Angat, which is 1,600 million liters a day for Manila, Manila water, and coming from deep wells or groundwater, around 3% of that comes from the groundwater. And of course, as I have mentioned to you, the water that is being delivered to the customers from around 440 million liters a day in 1997 soar up to 1,357 million liters a day in 2019. And as you could see, the water requirement based on the water delivered to the customers will be higher as we go along. But as you could see, the available water supply remains the same. So basically, the water that was being delivered to the customer was only taken from the water saved from the non-revenue water, because the non-revenue water program initiatives of Manila Water from the start, starting from 63% of losses of the water, we have put down the non-revenue water to 10% by 2010. So that is where we are now getting those sources for this increasing water water demand. However, we can also observe that the water demand has been increasing dramatically from 1997 to 2021, and new water source should have been delivered so that this could be sustained. In 2004, there is an issued moratorium on the use of deep wells in some specific areas in Metro Manila. So this limits our abstraction of water from the groundwater in Metro Manila. And in 2006, Manila Water has already attained the 24 hours water availability. And starting 2006, we now discontinued the use of groundwater in compliance with the moratorium that was provided by the National Water Regulatory Board. And the only wells that were operating were those wells in the Rizal area where our pipes have not yet reached the pipes coming from the water coming from Angat. So with the increasing water demand, this will not be enough just to rely on the non-revenue water that is being saved, since it is only limited to the available water from Angat. Based from our concession agreement signed in 1997, the concessionaires are not allowed to develop new water sources starting 2008, since the government promised to develop new source which should be operational by 2008. However, this water source has been delayed due to some challenges. It has moved from 2008, it was promised 2013, but later again it was moved to 2015, and then it was moved again to 2019. By the year 2016, Manila Water felt that the new water source will not be coming by 2019, while the water requirements continues to grow and will surpass the available water coming from Angat. Hence, Manila Water takes the initiative to look for alternative short to medium-term solutions to serve as a stopgap measures to address the water supply deficiency that is expected to happen in 2019. We hired consultants, and one of the things that we do is to have studied all the decommissioned wells to see if this can still be revived, and it's positive results that the water, the groundwater has been improving the static water level, and it can be used as a stopgap measures for 2019. In 2017, excuse me. Okay, in 2017, the Department of Interior and Local Government ordered the creation of water plan in preparation for the big one, the anticipated earthquake that would soon happen, because it's already 600 years old and the West Valley Fault line is expected now to move again and to have a major earthquake in the metropolis. So in preparation for that, the Department of Interior and Local Government orders the creation of water plan for the big one. And this includes the use of deep wells as a stopgap measure. And in 2019, the problem in 2019 is that the water source did not happen in 2019. So when the supply deficit occurred in 2019, Manila Water operated at least 39 wells to help alleviate the deficiency in the supply. It is where we were able to catch up because of the deficiency. And of course, the Cardona treatment plant, which we started to construct in 2017, studied in 2016, and constructed in 2017, and only completed in the middle of 2019. Okay. Unlike in other countries, Philippines is blessed with a lot of water, surface water. Okay. So the Manila Water aimed to have its water supply from the surface water. On the other hand, groundwater remains a viable solution and stopgap measure while waiting for the new sources to arrive. It can also serve as an interim source, especially when the big one or major earthquake hit the country. So in the short term, Manila Water has continuously conducted studies related to groundwater use. That's why we conducted the groundwater assessment, sustainability, and reliability in the East Zone concession area. And based on this study, upon comparing the groundwater heads in 2004, when the moratorium was provided by the National Water Regulatory Board, and looking at the data on 2014, the areas around Makati, Antipolo, and parts of Marikina indicate a gain in groundwater storage due to the rise in groundwater heads from lows of -50 to as high as 20. So there is an increase in the static head, maybe because the groundwater, the deep well, were no longer operated in these areas since 2006. Okay, and based also on that study, we conducted a simulation for 40 years. We tried increasing the use of groundwater by as much as 50% of the existing usage of groundwater in Metro Manila. And we found that there is no significant change in groundwater heads over the 40 years. For the East Concession, there is generally minor movement in groundwater level in Rizal. And this implies that the existing extraction rates are at quantities that do not over-extract to the extent of mining the groundwater supply. Also, we conducted studies, assessment of groundwater dynamics and water quality in the East Zone using the isotope and nuclear techniques. So we partner with the Philippine Nuclear and Research Institute, and we tried to study the groundwater using the isotope and nuclear techniques. And on that study, we have determined the groundwater age, or the one that we're pumping, and where are the recharge sources so that we can protect and for management purposes. Also, on the short term, we have a regular coordination with the MWSS, our principal, the National Water Regulatory Board, on the utilization of groundwater. We we submitted monthly the volume that is extracted, the groundwater levels, and the water quality that is being used, so that the NWRB could really manage the groundwater in Metro Manila. And we do not operate unless an authorization on the use of deep wells were provided by the NWRB. On the long-term action, we will rely mostly on the surface water. And new water sources will arrive in the coming years. This is already under construction. The 80 MLD Calawis in 2022, the 250 MLD million liters a day on East Bay, that is Laguna Lake, in 2023 and 2024. And the government project, which is the Kaliwa Dam, 300 MLD. Actually, this 600, but another 300 will go to Maynilad. So the 300 MLD will go to Manila Water in 2025. The existing deep wells will serve as a monitoring points for groundwater and aquifer water level and water quality. They will also serve as a backup sources, particularly in times of emergency, such as the big one, when most of the facilities or some of the facilities have been affected by the big earthquake. Then we have this deep wells on localized version that can serve the customers of Manila Water. So what are the key insights that we have taken on the utilization of groundwater? Number one is that the groundwater is an important supply of domestic water supply. It has been a key source in maintaining the 24-hour water supply in Metro Manila, especially as of today when there is still a deficiency in the total requirements of water versus the water supply during summer, when there is especially today at March, starting summer, we are now starting to operate at least 50 wells this summer, so that we could ensure that our customers still have a 24-hour water supply despite the deficiency in surface water sources. Also, the use of deep wells is anchored on sound feasibility studies and tests to ensure that over-extraction is prevented. Pumping tests are done to ensure extraction does not exceed recharge rates. So we just installed deep well pumps where we have conducted rigorous studies, sound feasibility studies. We conducted pumping tests. We checked the static water level and the drop in the water level to ensure that there is no over extraction that happened in all of those wells. Also, coordination with the key national agencies and local government units provided support in the use of groundwater. We really been coordinating a lot with the local government units, especially when drilling new wells, when operating new wells. There's a coordination that is happening always. And lastly, groundwater usage of Manila Water will continue even when there is already sufficient surface water. We will put standby wells in place of emergency usage, and we will also maintain this well so that whatever happens on the vicinity or on the locality, we could still have something in place to operate in case there is some problems that happen in the surface water. And I think that's all that I can share. So if you have any questions, we are ready to answer your questions. Thank you.
Thank you very much, Sir Noel, for that excellent presentation. And we learned a lot about Manila Water and Manila Water's activities and work in the past 25 or 24 years. Okay, so let's proceed to our next speaker. By the way, we already received a few questions, some questions. Later on, let's discuss all together after we finish all of the presentation. So for now, I would like to introduce our third speaker. Okay, so our third speaker is Steven Trincos. So he's going to talk about bioretention and permeable pavements. And this could serve as, an approach in order to recharge our groundwater. So Mr. Trincos is a licensed professional engineer in Connecticut. Since 1988, he practices in the land development field and is an internationally recognized expert in the field of low impact development. He has presented on many aspects of LID in Taiwan, China, and South Korea since 2011, and this time, first time in the Philippines, as well as many professional conferences in the United States and abroad. He has also presented at St. Andrews University in Scotland and has a Bachelor of Science in Forest Management from the University of New Hampshire. Let us all welcome our third and last speaker for today's webinar. Stephen, the screen is yours.
Good morning and good evening to everyone. It's a pleasure to be able to be part of this webinar and talk about this topic. So we're going to talk about recharging groundwater and how using the two primary systems of LID, bioretention and permeable pavement, can help recharge the groundwater so the water becomes cleaner and then is available for reuse. I won't go through all this as Marla has already done that. If you have questions, feel free to email me. I'm always available to answer questions, if they come up. So, what is groundwater? I think we've heard this, earlier, but basically it's rainfall that infiltrates the ground surface to the shallow and deeper groundwater tables. Shallow groundwater tables are in the soil. The bedrock aquifers are below that. Many individual wells here in the US have to be drilled into the bedrock. For potable water, we're not allowed to draw from the higher water table for residential use, but big commercial wells can be in stratified drift, which is the gravel aquifer areas. Basically this shows what happens when it rain falls in a natural environment. You've got, groundwater infiltrating the upland soils. You get it from, areas close to the stream. The streams can also provide infiltration. The trees take up water, and it works very well. The problem is, when we get what is groundwater, first off, groundwater is stored in the voids between soil particles and cracks in the bedrock, and basically it's the primary source is infiltration of rainfall. As we develop, however, we start covering the ground with impervious surfaces such as pavement, buildings, sidewalks, which prevent infiltration. Thus, you're eliminating the rainfall that would have infiltrated, and therefore you can effectively lower the groundwater tables because you're still using the groundwater, but now you're not recharging the groundwater. Can the adverse impacts of development on groundwater be addressed? Yeah, they can be, fairly simply by using low impact development, or what is called LID, or what I term low impact sustainable development, because that's what we're really trying to do, is create sustainable stormwater management systems. Both bioretention permeable pavements are systems that are designed to infiltrate the water, filter it through a soil media or gravel layer, and provide recharge to that shallow groundwater table. We're going to talk about bioretention systems first. They're really simple. They're basically a depressed landscaped area that utilizes a soil mixture to filter the runoff and allow it to infiltrate underlying soils. Depending on the soils or the urban environment, you can have them with or without an underdrain. Smaller systems were commonly called rain gardens. I like using the term bioretention. It applies to both systems. You generally take runoff from roof areas or other impervious areas. You can also take water from your lawn, as an example, and have it directed to a bioretention system by grading. The ponding depths are generally fairly low, around 12 to 18 inches on average. Depends on the soil type. If you have soils with a higher groundwater table due to a hard pan layer, you have a shallower ponding depth. But if you're in sand and gravel, you could have a much deeper ponding depth. So how do they work basically? Well, water comes into these systems either from a pipe or from overland flow. They're dead level on the bottom. So, water comes in, it spreads out, and obviously as water spreads out, it slows down. you get sediment settling out because the velocities slow down. The water then begins to move through the soil media, which is mostly a sand mix. And they're planted, there is vegetation in them, hence the name bioretention. The bio is plants. And nutrients in the runoff is taken up by the plants and used for growth. And over time, as these systems mature, you get biological and chemical reactions within the plants and the soil media that will remove and assimilate many of the pollutants that we find in the runoff. Metals are generally trapped because they attach to fine sediment particles. So if you trap the sediment on the ground surface, you're effectively trapping metals. Similar to hydrocarbons, they are also trapped. There's been some research in the US that bacteria on the roots of plants over time start breaking down the hydrocarbons and actually use the carbon for growth and basically eliminate the hydrocarbon as a pollutant of concern within the soil. Finer grained soils, silt or clay, the void spaces are much smaller, so water doesn't move as freely. But you can design these systems for these tighter soil conditions. It's not a one-size-fits-all approach. It's a performance-based design where you investigate the soils and you design the appropriate system. Soil particles, basically there's really three different types. Sand or gravel is the top here where you can see the particles, you can see a lot of large void space between them. So the water moves freely through these materials through that void space. When you get to the silt in the middle, the particles are much finer, the void spaces are much smaller. Water still moves through that, but also water can also be held by capillary action to the soil particles itself. So when it's a dry soil, the water will kind of come into a silt, but it will saturate it, but doesn't really move anywhere. When you get to a clay soil, you get more of this horizontal soil particles with some void space, but there's very few vertical connections between these soil layers. You get these little slots between them. So the ability of rainfall to infiltrate from the top to the bottom is much slower. Not to say that clay does not infiltrate, it just infiltrates at a very slow rate. You have to look at the soil structure, granular or single grain on the left here. You can see the raindrops at the top, you see all the raindrops on the bottom. Water moves through both of these systems very quickly. When you get to prismatic in the middle, they're kind of vertical chunks of dirt, but there's void space that runs vertically, so water again moves through them. But occasionally you'll get these prismatic structures that are more horizontal, and then the water doesn't move as freely. Blocky is also where you get kind of chunks of dirt, but water still moves through it, but again, not as fast as single grain or granular. Lastly, when you get to massive or platy structured soils, these are more your clay soils, you see a lot of rain on the top and very little coming out the bottom because, again, it's held by capillary action within the soil particles, or you have, in the case of platy, you have very little gaps moving vertically. So, the water may start coming in on the left, then have to go all the way to the right to find another gap to go down. So it takes a long time to move through a platy soil. So, what is a bioretention system? This is a very simplistic but commonly used one. It's basically, a dugout hole. The shape is highly variable. There's not a one size fits all. Generally, the ponding depth above the soil media is 12 inches. You have 2-to-1 side slopes. We have our soil media and we have our natural soils. So rainfall comes in, fills up to this ponding depth and simply infiltrates through the media and then infiltrates into the underlying soil. So you're filtering the water and then you're putting it right back into the ground. So you're reducing runoff volumes, which are the big driver of flooding. It's not the rate of runoff, it's simply how much water. So if we can infiltrate water, not only do we recharge the groundwater, we also reduce surface runoff and therefore reduce flooding potential. In some cases, you may have an underdrain. So we have, again, our runoff coming in, our ponding depth, our media. We have a small layer of pea gravel to separate the sand media from a coarser stone underneath. And we have an elevated underdrain pipe so that we're still having infiltration occur. But if we get larger storm events, it will fill up the stone layer and hit the outflow pipe and then be discharged to another stormwater management practice. This is common in some of the siltier clay soils where you don't have a fast infiltration rate, but you do want to have infiltration be the primary driver. But in the event of large rainfall events or short duration, high intensity storms, you have the overflow pipe via the underdrain. So what do they look like? This is one in my own house in the upper left here. This is off the end of my driveway. It gets about 3,600 square feet of roof area or pavement. And this is about 36 square feet is the surface area. And this is planted with these turf grasses that get very big and bushy. And the added benefit of these are you have a high surface area of grass on the leaves, and therefore you get more evapotranspiration from that system. The picture on the right is a bioretention for the roof drains from half of a roof of a commercial apartment building here in Connecticut, very densely vegetated. This was put in right after the building foundation went in so that it was seeded and it was all vegetated when the roof drains were actually connected to it. Another one at the end of my driveway, I actually cut a notch in the end of my driveway with a power saw. And the key thing here, when you create a notch along the curb line, the notch actually dives down into the bioretention cell because you have to give the water along a curb line the hydraulic gradient to tell it to make a left-hand turn here. If you just cut the notch dead level, that water will keep going down the curb. But in my case, the water comes along, the notch dives downhill, so the water says, "Ooh, that's the path of least resistance," and goes in there. And again, you plant them with many different species. These are all upland species. They are not wetland species, but they can take temporary inundation of 24 hours or so. And otherwise, the system is dry. So you can plant them with any type of upland plant that you want. Some ones that we did in a town to address water quality impacts to a lake. It's in the background here. This gets parking lot water from the corner of a paved parking lot down a riprap swale. We also have a grass swale that goes back uphill to another low point. These were taken the fall after they were installed, so that's why the vegetation is not very robust at this point. We have an overflow pipe here that we would allow the water to pond up a foot, and then it would be discharged anything beyond the foot. But we had very well drained soils here, and so far that pipe has not even gotten close to being utilized. Another one for both tennis courts and a basketball court, is for the same facility. And again, everything is infiltrated so far. These overflow pipes in a year and a half have never seen water. Another one for a roadway, we put a grass swale in just below this utility pole to take water from the curb line to bring it into the bioretention cell. And again, it's kind of a funky kidney shape, I guess, for lack of a better term, but this one's more grass with a native conservation seed mix. And again, will grow up much taller plants. This was taken about 4 months after it was seeded. So, how do you build these? Well, this is the one at my house again. First off, this was kind of it was a retrofit. So basically I just painted it out and then started digging by hand. And I found I had kind of fairly compact soils on top. And you keep going and you finally get down to what I term the underlying native soils, which is a yellow brown, fine sandy loam soil. And, there's a little bit of smearing, which indicates some silt. The picture on the right is a better picture showing that. And at this point, we did two things. I dug a hole with a post hole digger to make sure I had no indications of seasonal groundwater within 12 inches of the bottom of this, which I did not. And then using a Turf Tech infiltrometer, we ran double ring infiltration tests and got a pretty good rate in this soil. And one of the aspects here that's important is you can see the soils are kind of smeared here, and that's just from walking over them. So this is not a pure sandy loam. It's a very fine sandy loam, almost to a silt loam, but it does infiltrate very well. So the next step was taking a garden rake and removing all of that silty layer of soil, both on the bottom and the side walls of the system. And then the picture on the right is this is a sand mix. This is a washed concrete sand that we use. and we mix it with leaf compost, the bottom of a pile of leaves out in the woods. Typically, you'd mix this on the pavement and put it in together. I didn't do that. I put the sand in first, put the compost in, and then basically use the pitchfork to till the compost into it. And then I planted it. And then I had to water it for the first 30 days because it did not rain for the first 30 days after I built the system. But now it's self-sustaining, with the plants and the runoff going in there. So some other new ones that are down near Yale University. Again, you can put stones on the bottom with the native plants. We don't really use a lot of mulch on the bottom of these systems because mulch is wood. Wood floats up when it ponds, but then the mulch never kind of goes right back down to where it came from. So you can get areas with no mulch and you can get areas that are 4 or 5 inches of mulch. So it's becoming more commonplace to either just leave bare soil or they put in this river rock, more of a rounded rock, as something attractive for, the bioretention cell. This goes back to that apartment building. This is the bioretention cell, and the only spillway is a riprap spillway at the end, about 2 feet above the bottom here. The soils on this site were very well drained sand and gravels, and it has never gotten anywhere close to the spillway. The most water I saw out here right after a rainstorm was about 3 inches, and it's never gotten higher than that to my knowledge. So the other infiltrative practice we can use are permeable pavement, porous concrete, or open cell paver systems. Basically, what they all are is a type of hardscape that allows water to infiltrate through it. And therefore, it doesn't generate runoff. The runoff goes down through it. This is a detail from the University of New Hampshire Stormwater Center. For both for permeable pavement or porous concrete, it's a 4-inch layer typically. There's a layer of 3/4 inch wash stone. And then this filter course, this is a layer 8 to 12 inches thick of bank run sand and gravel. This is a native material, and this is what provides the water quality treatment within a permeable pavement system. Another layer of fine gravel, and then if we have, in this case, we have an underdrain with a coarse gravel layer, but again, infiltration is the primary driver. We do not put layers of filter fabric or line these systems unless you're in a situation where you simply don't want the water to infiltrate. It can be used for water quality and not for infiltration, but for the most part, we let the water filter through and we let it go into the underlying soils. Generally you have a 3-foot separation or roughly a meter from the bottom of the practice to seasonal groundwater to have an unsaturated zone. Most of the time they're on slopes less than 5%, but we can go up to 10% with design modifications. Native soils to have a 1/2 inch or basically 1.25 centimeter per hour infiltration rate. This means in a 24-hour period, you'll have 30 centimeters or 1 foot per day infiltration rate. So if you had a foot of water, in theory, with this infiltration rate, in 24 hours after it ponds, it will drain back down to the soil media. Most of the time, these systems have to be in what's termed a class A or B soil. Here in the US, these are well-drained sand and gravels or very sandy loam. And they need to be designed to drain down, basically to be dry or fully infiltrate within 24 hours after the rainfall event. So different types of systems, we get paving stones where in the corners are diamond-shaped cutouts, and these are all filled with pea gravel. So the water is not infiltrating through the stone, it's infiltrating through the gaps at the corners. You can also have PVC grids with crushed stone. This is a 3/8 inch stone, relatively small. Some cases we use the open cell pavers with topsoil and grass. This is not a great example because the topsoil is filled up to the top of the concrete paver. And so when a car is driving over it, not only are they driving on the concrete, their tires are also touching that soil. So the soil layer in these little cups gets compacted and you don't get good grass growth. With these systems, the topsoil should be a good 1/2 inch, or I guess, let's see here, 1.25 centimeters down below the top so that the grass grows up through, but then you're not driving on the soil and compacting the soil. The picture in the lower corner here, shows kind of the grass, growing, and it's not very robust, but the infiltration again occurs within those cell areas. So, interlocking pavers, are a good product. Again, we have, different layers of gravel for structural support and a deep gravel layer with an elevated underdrain. So again, infiltration is the primary driver, and then overflow or larger storm events go to the underdrain. Typically, we do not put in geotextile fabrics now. They can potentially clog, and then you got to dig up the whole system. So I don't bother using them. Again, this one is, paver stones. A lot of times you'll see these systems with sand between them, but sand gets clogged very easily by other organic material. When you use the fine gravel, if you do get clogging from organic debris, you can basically use a small walk-behind push vacuum that you can suck out the first quarter inch of gravel here, and you can then wash it and wash all the fines out of it, and then put it back, and you're back to a good working system. But sand between these are problematic because the sand can clog, and then you don't get any infiltration through these gaps. Again, a larger paver system, again, keeping the stone below the pavers. You want to drive on the concrete, not on the stone, because even fine stone will get a little compacted, if everybody's driving a car over it all the time. This is a picture of what porous asphalt is. I mean, standard asphalt, this would look very, very smooth. Here you can see all these different little void spaces. I like to use the analogy that permeable asphalt is kind of what I used to make as a little kid with a popcorn ball, where you use a K-Rose syrup that was kind of a sticky syrup that you boiled, and you mixed it with the popcorn, and then you formed a ball in your hand. So the syrup glued the kernels together, but you had all this void space. That's pretty much permeable pavement is. It's regular asphalt minus the sand. This is a apartment building, again, the same one with bioretention cell here that's on the left. This was 2 days after it was put in, and during a rainfall event. It's been raining about 3 hours at the time this picture was taken, and there's no water ponding. It's raining, but it's just infiltrating. This was the same parking lot a few years later, actually in December of 2014, slightly over a 1.1 rainfall event. And there's slope on this, and I'm standing in the left-hand picture on a curb at the bottom. And this water was running down the driveway, but it was infiltrating as it ran down the driveway because it never got to the curb that I was standing on. This was during a fairly intense rainstorm on the left, but as the intensity dropped, the picture on the right was taken, and basically the drying area, the area that's infiltrating, just got larger over time as the intensity of the rainfall lessened. Another apartment building, again, this is permeable asphalt. The entire parking lot was done this way. This is during, again, the rainfall event in December of 14. It's rained for about 5 hours at this point, and there's no runoff, coming off the pavement. To show you the difference, the beginning part of this driveway is standard asphalt, and you can see it here on the picture on the left, where the water's ponding on it. The picture to the left-hand side, that's permeable asphalt, and there's no water ponding. And the picture on the right is just an enlargement of that. So this shows how well permeable asphalt can infiltrate the water, and then it's recharging your groundwater. You're filtering it and you're putting it back into the ground where it can be reused by other users. And that's it. Thank you.
Oh, that's so nice. Thank you very much, Steve, for that excellent presentation. And we could see the application of LID in order, to help restore our groundwater sources. Based on the previous two presentations, we always try to use the groundwater as for water supply as our resource, but it's list that we think about how to replenish our precious resources. Okay, so may I invite all of our speakers to turn on their camera so we can have our discussion session now, to be moderated by Cruz. Okay, yes, there. Okay, there we go. So we've collected a lot of questions actually through private chat earlier. And now let's have our discussion session here.
All right. Thank you, Doc Marla, for the introduction. So we'll have some few questions to each of our speaker, and then later on we'll have some general questions to all of you. So I'd like to start with our first speaker, Sir Reggie Makasheb. So I think we have two questions for you right now. So the first question is, what are some unique challenges in conducting actual service for groundwater studies, considering that there are many variables to be considered?
Okay, so the first challenge is you have to complete. You need to have a rich collection of data in order to complete all those required variables needed in the modeling study. And when we did the modeling for Metro Manila, we really had a challenge of compiling everything. We actually have a lot of data from 1980s, 1990s, 2000 stored in the NWRB. However, it is not digitized. So you have to manually input it, manually digitize it so that it can be readily entered to the model. So that's the first challenge. The second is that when you do modeling, it is computationally challenging. So when you do it in your regular desktop, usually the runtimes would take. You are lucky if you'll have runtime of a few hours, but sometimes it would take days, especially if the dimensionality, meaning the number of variables, the number of cells in your model is many. Okay, is large. So that's the second challenge. But now I'm happy that there are high computing facility, okay, that are being high power computing facility that are being set up to accommodate these kinds of modeling projects, not only in groundwater but generally in simulation studies. Okay, so those two are the major challenges when it comes to groundwater modeling.
All right. Thank you, Sir Reggie. The second question is more on related to your current studies. So as you mentioned, you've been conducting a lot of studies related to visualization of groundwater mapping and all. So based on the results of your current studies and previous studies, what would be the possible intervention on high vulnerable locations in the Philippines?
Mm-hmm. Okay, so for high vulnerable locations, actually the intervention comes with the implementation of policies. We have a lot of policies in NWRB, in DNR, okay? But the problem is the implementation of those. For example, here in Metro Manila, it was mentioned earlier that there was already a moratorium on the construction of new wells, right? So when we identified those vulnerable regions, we know that these regions cannot take additional environmental stressors. So the moratorium must be continued in these particular areas. So those are some of the interventions. When it comes to saltwater intrusion, well, in Metro Manila, we do not have, at least 5 years ago when we did a study, we did not have a very problematic case in Metro Manila because a long time ago in 2004, the moratorium was implemented, so the intrusion has already been prevented. Okay, but if you are having problems with saltwater intrusion, one particular remediation is like the Henry problem I introduced earlier. You have to set or identify a recharge area in order to retard the artificial recharge area in order to retard the migration of salt water coming from the seaside to the inland aquifer. Okay, so basically those are some of the intervention.
All right. Thank you, Sir Reggie. So, and congrats, by the way, to the works that you're doing, that your team is doing related to groundwater management and visualization. So, my next question here is addressed to Sir Noelito Abesamis. So, one participant asked, with reference to water supply in the Philippines, how prepared are the current systems in place if the big one would occur tomorrow?
Thank you very much for that question. I think that's one of the items that really needs to be addressed because as we all know, we really do not know when the time when the big one will come. One of the items that we have looked at since 2017 with the coordinations with the Department of Interior and local government is to ensure that there is enough water to every locality. And the water that is during an earthquake, you should have seen the timeline. Once there is a big earthquake and some of the facilities have been destroyed, then it will take time for them to recover. So you should have at least 1 week or 2 weeks that enough water supply for the customers. So there are a lot of ways that we have been doing right now for Manila Water. One is we compute for the water requirements for drinking only, not including those being used for other purposes, but for drinking only. And based on the water requirements that is on the data that is available, it will show that we need to develop at least 115 million liters a day of water that should be available when all the facilities are down. And that means if we will be looking at the groundwater and assuming that the groundwater has only 1 million liter a day on the average, that you need 115 wells. And that should be strategically located at some point. So as of today, Manila Water has already built around, has already been operationalizing around 39 wells or 50 wells right now in standby and in operations. And but the capacity of those wells is around more than 1 MLD. So by the middle of this year, we will have an available of 100 plus 110 million liters a day of water, just enough for have those a few weeks or 1 to 2 weeks for supply interruption. And parallel to that, we are also installing groundwater reservoirs at some strategic points located on those areas like the one that is being used during where people during time that there is a disaster, people goes to this certain place like a building or a gym. We have already put at least 1 or 2 reservoir under the gym that we can pump during time of and this is not yet enough. We are looking at around 20 locations. More or less, we will be there by this month on the number of volume, but on how to really work at it together with the National Water Regulatory Board to allow us to do those and also the LGU, because it takes a lot of permits for us to do that. But for Manila Water, we can say more or less we are pretty well there.
All right, that's good to hear, Sir Noelito. And thank you for that particular answer. So I think we have a question here for Stephen. Hi, Stephen. So how do you address some apprehensions and concerns related to cost, including maintenance issues on the use of bioretention and, of course, permeable pavements?
Well, I mean, there's a lot of, unfortunately, a lot of misinformation out there that LID systems are highly expensive to maintain, require a lot of maintenance. And in reality, the opposite is true. Bioretention systems are relatively low maintenance. As again, you maintain landscape beds around your house or your business. You do the same for the bioretention system. You rake the leaves out or organic debris, once or twice a year. If they get a lot of runoff from the road, you may scrape the top quarter-inch off of this accumulated silt and you're back ready to work. Permeable pavements are a little bit more maintenance intensive. You do not put sand on them, but then again, I don't believe Philippines see a lot of snow in the majority of areas, so it's really not an issue in warm climates. They work well. Simply using a handheld leaf blower once a month, just blowing loose organic stuff off a permeable pavement is all you have to maintain it. Here in the States, when it's used in northern climates, we do not put sand on them at all. We just use chloride, but you can reduce the chloride application by 75%. And I know the New Hampshire Stormwater Center, they actually let a portion of their permeable pavement not be maintained for a couple of years. And then they looked at, well, what do we need to do to restore it? And they found with a regenerative vacuum, which is like a power washer with a suction vacuum, they could remove all the sediment and it was back to working normally. So, it's different maintenance, but it's not difficult maintenance. But, there's still a lot of misconceptions out there that lid is, more expensive to construct, more expensive to maintain. And the reality is completely opposite. They're much cheaper to install. And particularly the vegetated systems like bioretention are much less to maintain over time.
Right. So I think webinars and forums like this are very important for us to really inform the public with regard to this technology. So thank you, Stephen.
You're welcome.
So I think I have a question here for Reggie. So considering that there are current limited research on groundwater management here in the Philippines, because it's quite a difficult area to be studied, can you share to us what are the future research trends and areas? For example, I think majority of the studies are only focused in Metro Manila and I think in Central Luzon. For our researchers out there listening to us right now, what are the potential and possible areas for research that could you suggest?
Okay. So the current trend internationally, the research track about modeling is towards uncertainty analysis, risk management, and uncertainty analysis. Fortunately, in the Philippines, as you mentioned, it is not yet very well explored because it is a difficult research track to pursue. But the academe, the research community is now focusing on how to incorporate those uncertainties in modeling and how to incorporate those uncertainties in making decisions, because the managers are actually also at risk when they make decisions, right? Because when they implement something, when they implement a policy, they are accountable to that decision. And so the researchers have been exploring different algorithms so that somehow we can quantify the uncertainties that comes with groundwater modeling. And so when we implement policies, we can also inform the public or the project proponent how reliable these decisions are. So that's the future trend of research. Aside from that, by the way, that's called modeling with uncertainty. Okay, you might want to research that in various journals. Modeling with uncertainty or optimization under uncertainties. Okay. Aside from that, still the ongoing problem with modeling is the computational expensiveness of conducting a model. So there are new algorithms that are being explored on how to simplify the computational requirement of modeling. One example is by sampling the parameters, okay? Meaning you do not necessarily need to include all the data that you have gathered. You just need to sample what is the most likelihood parameter values, okay? That would be, that would affect or where the model would be most sensitive to. Okay, so that's one. What else? Well, basically those two are the major research tracks nowadays. Okay.
Right.
In the context of the Philippines, as I mentioned, we still have to perfect our understanding, our technical expertise on modeling.
Right, I agree. And we really need more research related to groundwater modeling and of course groundwater management. Thank you, Reggie. So I have a question here from I think one of the participants to Sir Noelito. He's asking with reference to the reports and information that you have presented earlier. Is Manila Water open for research collaborations and to access some of the information and data that you have presented earlier for research purposes?
Yes, we are open for research purposes. Actually, right now we are collaborating and partnering with Philippine Nuclear Research Institute for the isotope technology of studying groundwater using isotopes. We have also been collaborating with the University of the Philippines through Dr. Glenn Tabios and also to Dr. Soriano. We have a lot of studies that we are collaborating right now, even on those wells that we have really want to know if there is an incidence of the land subsidence. We would like to reduce or stop some of the usage of some wells on those areas. And not only on that, but we have a lot of collaboration with the different schools also, Ateneo and the other schools, with regards to some of the researches that we are doing on the environment. But that is you just need to look for people who are involved on those studies in our department so that we can really collaborate with it. If we have something to work at it, we are really looking for some people that we can collaborate.
All right. Thank you, Sir Noelito, and thank you for being open to any collaboration for us to really advance groundwater management here in the Philippines. So there's a follow-up question, by the way, to Steven with regard to bioretention. One participant is asking, do you recommend bioretention or permeable pavement in tropical countries or tropical climate like Philippines? Or do you have any other LID recommendations applicable for this type of climates?
Well, I based on my experience in South Korea, which has been very hot and humid weather, they're using both permeable pavement and bioretention there without any issues. So I would suspect if similar conditions in the Philippines, you could use them very easily. There's also what's called bioswales, which are swale systems with the bioretention media, which water, it's a conveyance system, but it's also an infiltration practice. So it's all driven by the soils that you have on the site. These systems will work in virtually all of them. They just have to be designed accordingly for the particular soil type. The better drained soils, it's very easy to do. When you get tighter soils, you've got to modify it, but you can still use them. That's one of the beauties of LID is it's a performance-based approach to stormwater management. It's not prescriptive like many regulations that say, you put a catch basin here, you put a detention pond here. LID is a whole different way of looking at stormwater, and you have to incorporate it into your site design in the beginning. You don't leave it till the end, so you make it a hydrologically functional site. That's the whole key of not letting the water drain from one end to the other, but addressing it where it's being created. It's a decentralized system. So yes, it can be used really anywhere. They're using it in Australia, New Zealand. So it can be used anywhere in the world. It's being used in Europe. They call it, their program is Sustainable Urban Drainage Systems, or SUDS, but it can be used anywhere. There's no limitation to it.
Like the term performance-based approach. And with relation to that, or in relation to that, there's a follow-up question to Stephen. How do you see the application of bioretention soils in Metro Manila here in the Philippines, and also the challenges that will be faced since Metro Manila and nearby provinces are relying on additional sources for water supply, such as groundwater?
Yeah, I mean, a lot of urban areas, and I can speak to Seoul, South Korea, having been there, and even Busan, that are, highly urbanized areas. I believe Manila would be similar. In many of the urban areas, you may not be able to infiltrate the water, but you can at least filter the runoff from impervious areas, and then maybe convey it to a larger green space where you can infiltrate it. So if you had a park land, in the middle of the city, you could do bioretention, collecting water from sidewalks or roads, and then have a shallow pipe system to a larger bioretention system within an open recreational area. So, it's more of a challenge implementing it as a retrofit in urban environments, but that's one of the things that I love about it, because urban environments provide a big challenge, but there are ways to overcome it. And when you come up with a solution, it's really rewarding, because you're increasing the green space within the urban area. And again, you can infiltrate the water, maybe not to the same degree you want to, but you can get some infiltration. But if more of the wells are, say, located outside the city, you can, do smaller infiltration. There's areas that are recreational areas for people, but they can be used as infiltration practices, but you wouldn't know it. They're kind of designed as part of the landscape. So, there's a lot of options and approaches to incorporate lid in urban environments. It is a challenge, but there are ways to do it. You just have to get very creative, because you've got underground utilities, you have above ground utilities. Many sidewalks I've seen in Southeast Asia, are very wide. I mean, they're 12, 15 foot, which is, 3 to, 5 meters wide. You don't need that big of a sidewalk. So you put bioretention, on the meter or two next to the road. You take the sidewalk runoff into it, you take some of the road runoff into it, you have green space, and you also have a green barrier between the pedestrians and the road now. So, you can really make some very unique, concepts. Portland, Oregon has done a lot of what's called LID planner systems, which are systems, they're bioretention in the urban environment to do exactly that.
Right. So thanks, Stephen. And I think LID has a lot of potential, of course, in tropical countries like Philippines, because we have a lot of rains or precipitation coming in all year round. So we're expecting to have more research and projects related to the application of low impact development here in the country. So there are a lot of questions coming in, but we don't have enough time. So I'd like to give one last question to our three speakers. And of course, this is related to in celebration of the World Water Day. So just give us a brief answer to this question. Why is it important to make the invisible visible in the context of groundwater? Why do we need to focus now on groundwater? So can we start with Sir Reggie Makasheb?
Well, it is difficult to navigate and solve problems that we do not really understand. So we have to make the invisible visible.
All right. Thank you, Sir Reggie. How about you, Sir Noelito Abasamis?
Well, I think we need to really understand what's going on with all the things that we are using or developing, because we do not know if we are using it right. When we do not know, we cannot really understand what's going on.
Right, great. Thank you, Sir Noelito. Steven?
Well, they've actually taken the top two answers. But I would add to that because it's below ground, people think it's an infinite resource, and it's not. And all of a sudden, one day it becomes not usable, and that's when there's an outcry. And so, if we're proactive in understanding, the amount of groundwater and how it moves through the soils and the bedrock, and then can add water back into it, now we're going to make that resource a much more viable one over time.
Right. Thank you, Steven. So can we just give a virtual applause to our three speakers for their wonderful presentations and insights for today's webinar? So before we proceed to photo session, I'd just like to synthesize everything that transpired on this webinar. So basically, we're conducting this webinar in order for us to really mainstream groundwater management. So as we know, groundwater provides almost half of all drinking water worldwide, not just in the Philippines, and around 40% of the water used in irrigation and about 1/3 of the supply required for industry. And not only does groundwater sustain ecosystems, it is also an important factor in climate change adaptation, just like how our speakers have mentioned. And with the rise in water scarcity and the decrease in the availability of surface water, of course, due to human activity and some climate change factors, there is an increased reliance and pressure on groundwater. And during this webinar, I think we could all agree that we need a strong academic, government, and industry collaboration to promote a more holistic and evidence-based groundwater management practices. So again, let's make the invisible visible. So at this point, we would like to request the organizers, the participants, to open their camera for a quick photo documentation for us to have a good documentation for this webinar. All right. All right, requesting everyone to kindly open their camera. And I hope you all learned from the speakers that we have during this morning. And if you have more questions, you can send it to the organizers and we will relay it to our speakers. So I'll take some screenshots in 3, 2, 1, smile. Okay. One more. In 3, 2, 1. Last one for the last tab in 3, 2, 1. All right. So again, thank you very much, Doc Marla.
Yeah, thank you very much, Hiel. Also, we would like to request our, Mario is here, our participant. Let's spotlight for the photo session. Only the speakers and Mario and Hiel and me. Let's have a photo session, all of us. Can I request the support of Jay, please, to spotlight all of the speakers? Thank you. And Mario also. Okay, let's have a quick photo session. All right, we're ready? Okay, ready?
Sure.
Ready, 1, 2, 3, smile.
Jeez.
One more. 1, 2, 3, smile. Yes, that's all. Thank you very much, everyone. Thank you to all who attended and also to those who are still watching in Facebook. Thank you very much. Thank you, Hiel. Thank you to all of our speakers. Maria, thank you. And I would like to invite everyone next week. We have our here fireside chat about groundwater. Again, this is the second part of our celebration of World Water Day. So we invited really excellent speakers. So please join us again next week. Bye, everyone. Thank you.
Hi, thank you.
Bye.
Thank you.